Good morning, class. Today is December 16th. I promised that I would give you somewhat of a test review today. I didn't realize you wouldn't be meeting with me today, so I'm going to record this session and post it to the page later today. You'll have to excuse me, I'm still trying to recover from an illness that I contracted last week, so my voice is still kind of out of commission. But I'm going to try my best to get through this. So if you remember from last time we met, last Tuesday, we mentioned there being a final exam for this class. Not really a big deal. It's only 27 questions long, all multiple choice / true false. That exam opened on Friday. I noticed that no one has taken it yet, and that's totally fine. Just make sure that you can get it done sometime this week. There's no time limit on it. Once again, all multiple choice, open note, open book. You can bring anything you want into it. The purpose for today's session is to give you a taste of the equations that you'll need for each question. And if you have questions, please email me or text me, and I can get those questions answered as quickly as I can. So let's go ahead and scroll down to the end of course tab on your class page. Just a couple of reminders. We did remind you about the project last week. So the current event project, it's a 100-word essay based on a news article that you find on Google News from the past week that's physics related. If you have questions on that, please email me. Here's the final exam. It's at the very bottom of this tab. It is open, so if you click it and start it, you can begin working on that whenever you'd like to. So without further ado, let's get on to the exam review, which I prepared for today. So I sent this review out on, I believe, Tuesday of last week. So you've had it for, about 5 or 6 days now. But I thought you might benefit from seeing some problems laid out for you with the equations you'll need and with some hints. So I've already attached this document to the course page. Let me show you that real quick, actually. So under my usual messages that I send you guys on a weekly basis, I put the study guide right up here at the top of the course. So you can find the document we're going to go through right now attached to your course at that location. Okay, so there are 27 questions. The questions that I've pasted into this document parallel the questions that you'll see on the exam. Pretty exactly, if I might add. The only thing I might have switched out were some numbers, just so I could test you guys on your ability to use the equations correctly. So we're going to get started. There are 3 topics. There are 3 questions from each topic. There are 10 topics total. I think I removed a couple questions from topics 9 and 10 that I didn't feel were too important for you to know at this time. So it was 27 questions. So here we go. Topic 1. We've got American football being played on a 100-yard long field, excluding the end zones. How long is the field in meters? Assume that 1 meter is equal to 3.281 feet. Okay, so this is a simple conversion problem. I've typed my little hints to you in blue italicized text. So my hint to you is here to use dimensional analysis to help you in conversions. Okay, so I'm going to go ahead and sketch this out real quick. Pardon my bad handwriting with a mouse. So we have 100 yards. They tell us that we're trying to get to meters. Okay, so what I know about yards, I know that in 1 yard, there are 3 feet. Okay, so you can see me breaking out the dimensional analysis with my ratios right here. The problem told me that 1 meter is the same thing as 3.281 feet. So I could say, okay, well, for every 3.281 feet, I have 1 meter. Okay, now you'll notice that the reason we do dimensional analysis is that you can see the units will cancel. So yards are gone, feet cancel, which means I'm going to be left in my desired unit of meters. So because that checks out, let's go ahead and calculate. So in my calculator, I'm going to do 100 times 3. I'm going to divide that by 3.281. Okay, so I've got my calculator right here. So we're going to do 100 times 3. We're going to divide that by 3.281. My answer is about 91.4 meters. Okay, so 91.4 meters. And that's your answer. Okay, so just a simple process of dimensional analysis, and then you're done. Let's go ahead and go on to number 2 now. Okay, what is the area of a circle in 3.12 centimeters in diameter? Express your answer to the correct number of significant figures. So this question, as it states, is designed to assess your guys' knowledge of significant figures. So I even give you the formula for area of a circle right here in case you forgot it. But my little tip to you for now is that there is a rule for when you're multiplying sig figs. So here I typed it for you. When multiplying sig figs, your answer should have the same number of sig figs as the least precise measurement, okay? So when you think about the measurements that are involved in this problem, we gave you 3.102 centimeters, which is the diameter of the circle. We also told you to use 3.14 as an approximation for pi. So out of these two measurements right here, 3.102 and 3.14, you'll notice that pi only has 3 significant figures. Okay, so 3 SFs, okay? Whereas the diameter has 1, 2, 3, 4 significant figures in it. So because pi is the least precise of those two, we are gonna base our answer on 3 significant figures. Okay, so let's go ahead and plug our information into our formula, excuse me. So area is equal to 3.14. We're going to times that by the square of the radius. So to get radius, we'll need to take our diameter right here and cut it in half. Okay, so 3.102, let's bring up the calculator. If I take my 3.102, 3.102, divide that by 2, it gives us a radius of about 1.551. Okay, so 1.551 is what I'm going to plug in for my radius, and we're going to square that. Plug all these numbers in, you're going to get your answer for area, and then we'll discuss the rounding. So we're going to take our 3.14, we're going to times that by 1.551 squared. Okay, so I'm going to hit my exponent button, I'm going to hit squared. So the answer that I get is about 7.553-ish. Okay, so now notice we have a long answer here, but we just said in the problem we have to base our answer around 3 significant figures right here because that was the least precise number that was given to us. So I'm going to cut this answer off at 3 sig figs, and because this 3 is going to influence how this 5 is rounded, back to your rounding rules from elementary school, we're going to round that 5 down because that 3 is less than 5. So your answer should be 7.55 centimeters squared. And that would be your answer. Okay. Let's keep going. Let's keep going. Okay, next question. How many significant figures are in the numbers 99 and 100? So for your convenience, I try to make the rules for significant figures pretty concise here. I've written 4 rules for you. So rule number 1, all non-zero numbers are significant. Okay, if it's not a 0, and if it's any other number, it's going to be significant. If you ever have leading zeros, they are never significant. So any zeros that are found at the very front of a number do not count. Trailing zeros are only significant if a decimal is present. So if you don't have a decimal point and you have a trailing 0, it's not going to be significant. And last but not least, sandwiched zeros are always significant. Okay, so let's take a look at these rules in the context of an example. So how many sig figs are in the numbers 99 and 100? So let's start with 99. So 99, you'll notice there's no zeros in 99 at all. So 99, we're going to evaluate using rule 1. Okay, so because all non-zero numbers are significant, I've got a non-zero digit right here. I've got a non-zero digit right here. There are 2 digits there. So we're going to say, okay, there's 2 sig figs in 99. Okay, so let me group these together just so we don't get mixed up. So 99, there's 2 sig figs. When we look at 100, however, we can definitely see some zeros there. So the question is, are they leading zeros or are they trailing zeros? So because the zeros come at the very end of the number, they are going to be classified as trailing zeros. And notice the rule says that trailing zeros are significant if a decimal is present. I don't know about you, but I do not see a decimal point in this number that I gave you, 100. So because there is no decimal, those zeros will not count as significant. Okay, so which means only the non-zero number will be significant. So in 100, believe it or not, there is only one significant figure. Okay, and it's just that one. The zeros do not count. So that's pretty easy. Let's keep going. Okay, topic 2. On May 26, 1934, a streamlined stainless steel diesel train called the Zephyr set the world's nonstop long-distance speed record for trains. Its run from Denver to Chicago took 13 hours, 4 minutes, 58 seconds, and was witnessed by more than 1 million people along the route. The total distance traveled was 1633.8 kilometers. What was the average speed in kilometers per hour and meters per second? So for your convenience, I've attached the formula for speed, for average speed right here, and that is average speed is equal to total distance traveled divided by the total time. Okay, and we want the speed in kilometers per hour and then in meters per second. So let's do kilometers per hour first. Okay, so we know that speed is going to equal distance traveled divided by time. And conveniently for us, they gave us the distance traveled as being 1633.8 kilometers. Okay, now the problem is that in order to calculate kilometers per hour, we need hours. But the time units that they gave us were a mixture of hours, minutes, and seconds. So we need to consolidate those all down to be 1 unit of time. Let's do hours since that's what we're going for in our first part of the question anyway. So 13 hours I can leave alone because it's already in hours. Let's say I wanted to convert 4 minutes into hours. Okay, so if I take 4 minutes and I realize that for every 60 minutes, there is 1 hour, I can use some dimensional analysis to go ahead and calculate this. Okay, so 4 minutes times 1 hour divided by 60 minutes. Let's whip out the calculator real quick. So 4 divided by 60 tells me that I'm dealing with about 0.067 hours. Okay, so that's 0.067 hours. Let's do the same thing for the seconds. So they gave us that there were 58 seconds involved in this journey. Okay, I know that there are 60 seconds in a minute. And we just set up above that for every 60 minutes, there's 1 hour. So the conversion is going to go something like that. So whatever 58 times 1 times 1 divided by 60 times 60 is, that's going to be my answer. So I know that 58 times 1 times 1 is going to be 58. On the bottom, 60 times 60 is 3,600. So whatever the quotient of 3,600 and 58 is going to be our hours. Okay, so let's whip out the calculator again. Okay, let's move this out of the way. So I'm going to take my 58, I'm going to divide that by 3,600, which tells me I'm dealing with 0.016 hours. Okay, so 0.016 hours. Let's go ahead and add our hours with our hours that were already given to us. So we're going to have 13 hours plus 0.067 hours plus 0.016 hours, and that should give us the grand total time in hours of our journey. Okay, so 13 hours plus 0.067 hours plus 0.016 gives us a grand total of about 13.083 hours. So 13.083 hours. Okay, so let's go ahead and plug that in down here. Okay, so 13.083 hours. So if I take the quotient between those two units, that should get my speed in kilometers per hour. Okay, so Let's go ahead and clear our calculator. I'm going to type in 1633.8 divided by 13.0, oops, wrong, extra zero there, 0.83 hours. And I get about 124.88, let's say, meters per second. Okay, so 124.88 meters per second. So that's the answer to part one of the question. They also wanted it in meters per second. So after this, I would proceed to basically convert meters per second into, oh my goodness, I'm all over the place today. This isn't meters per second. This is kilometers per hour. Sorry for the confusion. This is kilometers per hour. And we want to get that to meters per second. Okay, for the sake of time, I'm just going to set it up for you, and you can go ahead and calculate it on your own if you'd like. But basically, the dimensional analysis is pretty straightforward. I can keep going with my conversion chain and say that for every 1 kilometer, oops, that's a huge one. For every 1 kilometer, there is 1,000 meters. Okay. And like we said before, if you remember, for every 1 hour, we have 3,600 seconds. Okay. Now remember, the whole idea of a dimensional analysis is to make sure units cancel. So you can see kilometers are canceling, hours are canceling, which means we're going to be just left with meters over seconds. Okay, so I'm going to leave this up to you, but you're going to type into your calculator 124.88 times 1,000 times 1 over 3,600 seconds. And that should get you to your speed in meters per second. Okay, that was a little drawn out. It's kind of a math-intensive problem, but it's not too bad. Let's keep going. Next, assume that an intercontinental ballistic missile goes from rest to suborbital speed of 6.50 kilometers per second in 60 seconds. The actual speed and time are classified. What is its average acceleration in meters per second squared and in multiples of g? Okay, so I've given you the formula down below. Remember that average acceleration is equal to final velocity minus initial velocity all over time. Okay, so it's just a matter of plugging these things in real quick. So my final velocity is 6.50 kilometers per second. My initial velocity, I have to infer a little bit. They said it started at rest. Okay, so my initial velocity is going to be 0. So if I take my 6.50 and if I minus away my initial velocity of 0 and divide that by the total time of 60.0 seconds, this should give me my, sorry, I think one thing I forgot to do is convert to our standard units of meters per second. So what I should have done is taken my 6.50 kilometers per hour, or kilometers per second, excuse me, and convert that to meters per second. It's not too hard. Let's do it real quick. So 6.50 kilometers per second. I know that for every 1 kilometer, I've got 1,000 meters. 1,000 meters. So it's just moving the decimal place over 3 times. That's going to give me 6,500 meters. Okay, so that's the number that we're going to use to plug into our formula. I'm going to type this out just because it's a little bit faster. So based on our formula right here, our final velocity we just said was 6,500 meters per second. We're going to minus away our initial velocity, which was at rest, which is 0 meters per second. And we're going to put that all over our time unit. Okay, and our time was 60.0 seconds. Okay, let's whip out the calculator real quick. Okay, so on our calculator, we're going to hit 6,500 minus 0 divided by 60 seconds. That gives me 108.33 meters per second squared. So that's my acceleration. Okay. Let's type that out. 108.33 meters per second squared. Okay, so that's our answer for the acceleration. Now notice the problem also asks us to calculate it in meters per second squared, which we've already done. It also asks us to calculate it in multiples of g. So how many times can g, which is 9.80 meters per second squared, go into our answer of 118.33? So to calculate that, all we got to do is take our acceleration and divide it by g. So if I take this thing and I divide it by 9.80, we're going to see it's about 11g. Okay, so for my answer, I put or 11g. So this would be your answer right here. Okay, let's keep going. All right. So you'll notice in this problem, I've provided you with 4 different equations. You're not going to have to use all 4 of them, but I just wanted to show you all the kinematic equations we learned so you can see how we go about selecting which one we need to use. So the problem states that in a slap shot, a hockey player accelerates the puck from a velocity of 8 to 40 meters per second in the same direction. If this shot takes 3.33 times 10 to the minus seconds, calculate the distance over which the puck accelerates. Okay, so things that I can see here, they're giving me an initial velocity, they're giving me a final velocity, they're giving me a time unit, okay? They're looking for distance, okay? So if they're looking for distance, 2 equations jump out at me from the get-go. This one looks at distance, this one solves for distance as well. Okay, so I know I'm probably going to use one of those 2 equations. The only thing that's kind of making me lean towards one over the other is the fact that they mentioned that the puck is accelerating. Because the puck is accelerating, I'm kind of leaning more towards this one because it has an acceleration unit inside of it. Okay, but the problem is they didn't tell us what the acceleration was. So in order to figure out what the acceleration is, we can use another equation. Okay, remember that acceleration equals VF minus VI over T. We did that in a problem not too long ago. But basically what I'm saying is you can take this equation down here, get A by itself, and then solve for A using this problem. Okay, so based on what we did a couple problems ago, I told you that VF minus VI over T is acceleration. Okay, so let's figure that out first. So my final velocity is 40 in this problem. My initial velocity is 8. And this is all happening over a time span of 3.33 times 10 to the minus 2 seconds. Okay, so let's go ahead and plug that in and see what we get. So get calculator. Here we go. So 40 minus 8 is 32. I'm going to divide 32 by 3.33 times 10 to the negative 2nd power. Okay, and that should give us our acceleration. Okay, so our acceleration we just calculated is 960.96 meters per second squared. Okay, now as I stated before, we can go ahead and plug our acceleration, recalculated here, into our equation for distance. So I'm going to plug it in right there, and that should give me the distance when I've already done all the math. Okay, so let's do this together. So distance should be equal to VI times T. Well, my VI we said was 8. We already know my T is 3.33 times 10 to the negative 2nd. Okay. Then we're going to add 1/2, so 0.5 times A, which we said was 960.96. I'm going to times that by T squared. So 3.33 times 10 to the minus 2nd, all squared. Okay. So it's kind of a long equation, but our calculator should make pretty quick work of this. Okay. So I'm going to get my calculator. I'm just going to plug everything in. Okay. So here we go. I'm going to take 8 times, in parentheses, 3.33 times 10 to the negative second power. Okay, I'm going to add on to that 0.5 times 960.96 times 3.33 times 10 to the negative second, and that is squared. When I do all that, I get an answer of 0.799 about. Okay, so my answer should be 0.799 meters. Let's see if that makes sense in the context of the problem. So keep in mind, this is about a hockey puck that's being whacked at with a hockey stick. Does it make sense that throughout this puck's acceleration, as the stick is acting on it, that the puck would move a distance of about less than a meter, 0.79 meters? Totally. That's probably a good estimate for how long that puck is going to be in contact with the hockey stick. So yeah, our answer makes sense. So just to sum it up, we had to pick the equations that would help us get to our the answer we were looking for. And once again, those equations, we had to figure out acceleration using this equation first. Then once we figured out the acceleration, we used it and plugged it into this equation for distance. Let's keep going. Okay. Now on to topic 3. So suppose you walk 18 meters straight west and then 25 meters straight north. How far are you from your starting point, and what is the compass direction of a line connecting your starting point to your final direction? Okay, and then here's a little hint for you. If you represent the two legs of the walk as vector displacements a and b, as in figure 2, this problem asks you to find their sum, r is equal to a plus b. All that's saying is that we're going to use the Pythagorean theorem. Okay, so remember from geometry, the Pythagorean theorem is that a squared plus b squared equals c squared. So they're telling us that we're walking 18 meters west. So that's like this leg of the journey right here, 18 meters west. Then we're going to be walking 25 meters straight north. Okay, 25 meters north. So if we're walking west 18 meters and north 25 meters, they want us to figure out what's the total displacement. What's this hypotenuse right here? Okay, so just like in Pythagorean theorem in geometry class, a squared plus b squared equals c squared. Okay, so if we're going to plug this into our calculator, I know that 25 squared plus 18 squared, so 25 squared plus 18 squared gives me this number, 949. Okay, so 949 is that total. And then, since that is equal to c squared, we need to square root that number to figure out what our hypotenuse is. So I'm going to take the square root of 949, which gives me about 30.8 meters. Okay, so that's equal to about 30.8 meters. So ask yourself if this makes sense in the context of the problem. If our westward leg was 18 meters, and we also walked 25 meters north, could this distance right here reasonably be about 30.8? Totally, totally could. Okay, so that makes sense. Now, the second part of the question asks us to calculate the direction. Okay, so you're going to need to break out some inverse trigonometry here. But basically, using the legs that were given to us, a little bit of inverse trig, we can say that the inverse tangent, remember from geometry, we use inverse trig functions to figure out angles. The inverse tan of our opposite over our adjacent side, this should give us what theta is. Okay, remember SOHCAHTOA, tangent stands for opposite over adjacent. So if we want to figure out theta, we got to do the inverse tan. Okay. If you have questions on the trig, or if you don't really remember the trig from geometry class, please let me know. I'd be happy to walk you through it. So I'm going to take my inverse tan, which on the Google calculator, trying to remember how we do this. Oh, I think it's this inverse button. Yes, good. So if I take the inverse tan, which is called the arctan rule of 25 divided by 18, that should give me my angle. Now, you'll notice Google gave me it in degrees of, in units of radians, but to make it more realistic, we're going to make this into units of degrees, which Google tells me is about 54 degrees. Okay, so I'm going to put my answer as about 54.2 degrees. Once again, you can ask yourself if that seems reasonable. Could this theta, could this angle right here be about 54.2 degrees? Yes, it totally could. That's totally reasonable. So our answers are 30.8 meters and 54.2 degrees. Let's keep going. Okay, next problem. A ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. Ignore air resistance. How long is the ball in the air? Okay, so once again, we're going to look at our different equations here. We're going to pick out the one that seems the most appropriate. Notice they're giving us a distance. Okay, they're giving us, oh, by the way, it's a 60-meter tall building. So this is a vertical distance right here. I'll put a V there. They're also telling us a horizontal distance. So if we're throwing a ball from the top of a building, it's going to land 100 meters away from the base of the building. That's a horizontal direction the ball is traveling. How long is the ball in the air? Okay, so we're looking for t. So I need to look at equations that only deal with t. So I can pretty much cross out this equation. That's not going to be very much help to me since we don't really have t involved anywhere. Things that we can infer from the problem, by the way, we know that this ball is being subject to gravitational acceleration. So we know that a is going to be equal to negative 9.8 meters per second. Okay. We know that the ball was initially, so if you're throwing a ball horizontally off of a building, like let's say here's your building right here, and you're throwing the ball horizontally, understand that even though they didn't tell us how fast the ball was moving, when we talk about vertically speaking, this ball is only being thrown horizontally. So it's not really, it doesn't possess any vertical velocity at all. Okay, so keep that in mind. Its vertical velocity initially is 0 because the ball's being thrown horizontally. Okay, so I'm gonna make a little note here just so we can not forget that. So vertical velocity equals 0 because it's horizontal motion. Okay, let's go ahead and move this over out of the way a little bit. So if the vertical component of velocity is 0, my VI is 0. Okay, so let's take a stock of what we have. So once again, we're looking for time. We know the distance that travels vertically is 60 meters. Okay. We know its vertical acceleration is negative 9.8. We know its initial velocity is 0. So this equation right here is popping out as one that could help me. D I already know is going to be 60. VI is 0. T we're looking for. Then we have 1/2 times A, which is negative 9.8, and then T squared, which once again, we're trying to solve for T. So this equation looks pretty promising. Let's go ahead and type everything in that we need. Okay, so we know that D is going to be equal to negative 60 since the ball is falling 60 meters total. Okay, it's going to be equal to VI, which we said was 0 vertically speaking, times T, which we don't know. Add that to 0.5 times negative 9.8, that's our acceleration, times T squared. Okay, and as we start to try and figure out what T is, realize 0 times anything is going to go away. Okay, so we're left with negative 60 is equal to 0.5 times negative 9.8 times T squared. So if we wanted to get T by itself, we would divide these two coefficients out of the way to the other side. So divide 0.5, divide the negative 9.8, 9.8, oops, that's a weird 8. Whatever you do one side math, you got to do the other. So divide by 0.5, divide by negative 9.8. 9.8. Those 9.8s are hard to write on mouse. Once we do this, we're going to get whatever t squared is. So let's get the calculator out. So I'm going to take my negative 60. I'm going to divide that by 0.5 times negative 9.8. And that should give me a t squared of about 12.24. So 12.24 is equal to t squared. Okay, we'll have to square root that answer. Okay, so if I take a square root of 12.24, I get that t is equal to about 3.5 seconds. Okay, so t is equal to 3.5 seconds. Now let's ask ourselves if that sounds reasonable. Does it seem reasonable that this ball will be in the air for about 3.5 seconds if it's thrown from a 60-meter tall building? Yeah, that seems pretty reasonable. I mean, we obviously won't know until we try it ourselves, but could you envision it taking about 3.5 seconds for this ball to fall to the ground from 60 meters? I don't know about you, but I totally couldn't envision that. Okay, so just to sum up, they gave us a horizontal distance right here. We didn't actually end up using it because we just examined the ball using vertical components. So the vertical distance the ball falls, the vertical acceleration, the vertical initial velocity. Okay, we didn't need to examine the horizontal motion at all for this problem. So that's kind of a distractor. Okay, let's do a similar question. Oops, and I might want to hold on to these numbers just in case I need them. So the second question I've got down here is the same question as before. It's just asking a different part. So we still got the same scenario, except that it's asking what is the vertical component of its velocity just before it hits the ground. So they want the velocity just before it hits the ground. So they're looking for VF. Okay, VF is what they're interested in this problem. So if I look at my equations that are available to me, the distance one doesn't really help me out because that doesn't have VF in it. I've got VFs in the remaining of 3. Really, I could take my pick and do any one of these. I'm going to do this one, though, just because it's got the most complete set of information. We already know the initial velocity was 0. We already know the acceleration is negative 9.8. We already know the distance it's traveling is about negative 60 meters. So I'm going to go with that one. Okay, so I'm going to plug what I know in. So VF squared, I don't know. That's going to be equal to VI squared, which is just 0. 0 squared, plus 2 times our acceleration of negative 9.8. Okay, times our distance traveled, which is negative 60 since the ball was falling downward. Okay, let's go ahead and whip the calculator out. So 0 squared is just 0. And then I've got 2 times negative 9.8 times negative 60. Okay, and I get that VF squared is going to be equal to 1176. Now, if I take the square root of that, that should give me what VF is. So let's do a square root. Square root of 1176 gives me a VF of about 34.3 meters per second. Okay, so VF equals 34.3 meters per second. Okay, this one's going to be a little bit more difficult to kind of gauge just thinking about this logically. So when I ask myself, can I envision this ball traveling at about 34.3 meters per second as it hits the ground? Kind of hard for us to envision that, but it's not a huge number. Remember that as we drop this ball, it's constantly picking up speed for every second that goes by. So if it's traveling 3.5 seconds and it's picking up speed for the duration of that 3.5 seconds, it's totally reasonable. It totally could work. Okay. Okay, let's keep going. We're already a good 30 or 40 minutes into this, and we're through topic 3, I believe now, on to topic 4. So I might need to split this video up into 2 parts to cover the second half of the review. We'll see how far we can get in the next 15 minutes, though. This is an easy one. What properties do forces have that allow us to classify them as vectors? So remember way back when, from topic 2, I believe it was, we talked about these things called vectors. And there were 2 things that made a vector a vector. Okay? Vectors, by definition, must possess magnitude. Oops, it's a little huge. Sorry about that. Let's put it down here. Magnitude is one of those components, and direction. Okay? So unless a quantity has magnitude and direction, you cannot call it a vector, excuse me. So that's what you got to remember. Vectors need magnitude and they need direction. Okay, on the next problem. A cleaner pushes a 4.50 kilogram laundry cart in such a way that the net external force on it is 60.0 newtons. Calculate the magnitude of its acceleration. Okay, so we've provided the relevant equation we need here. It comes from Newton's second law of motion, which basically says that the net force on any object is equal to its mass multiplied by its acceleration. Okay, so let's examine what they gave us in the problem. They gave us a mass of 4.50 kilograms. They gave us the net force of 60.0 newtons. They want the acceleration. Okay, so let's plug these numbers where they go into the equation. So my F net was 60. I know my mass is 4.50, and I don't know my acceleration. Okay, so how am I going to get acceleration solved for? This is algebra 1 stuff. Just divide both sides by 4.50. 4.50 divided by 4.50. That's going to cancel, and we're going to be left with whatever A is equal to. Okay, so on the calculator, if I take 60 divided by, oops, not 61, 60 is what I wanted. 60 divided by 4.50, oops, 4.50, I get an acceleration of about 13.333 meters per second squared. So A equals 13.33 meters per second squared. And that's your answer. Okay, so really just simple equation. This should be a very easy question on the test. Going on. Calculate the tension in a vertical strand of spider web if a spider of mass 8.00 times 10 to the minus 5 kilograms hangs motionless on it. So remember that tension is a type of force. Okay, so we can use Newton's second law just like we use in any other force problem. Okay, so remember that force is equal to mass times acceleration. Okay, you'll notice in this problem they gave us the mass of the spider. So that's our M. But you'll notice there's no acceleration given. So what's up? Can you solve this problem? Well, you can, because remember this spider is hanging motionless on a strand of spider web. So if it's hanging, that means it's being subject to gravitational acceleration. Okay, so you kind of have to infer that your acceleration is going to equal negative 9.8 meters per second squared. Okay, let's go ahead and plug in what we know. Okay, so we know we're looking for the tension, so we're looking for our force. We are being provided with a mass of 8.00 times 10 to the negative 5 kilograms, times that by the acceleration of negative 9.8 meters per second squared. And this should give us the tension. Okay, so I'll flip out the calculator again. Oops. Okay, here we go. So I'm going to do 8 times 10 to the negative 5. And I'm going to times that by negative 9.8. Okay. That gives me 0.000784 newtons of force. Okay. Now, the spider is exerting a downward force of negative 0.000784 newtons. Okay. But keep in mind the tension of the rope, or the spider web, excuse me, the spider web is pulling up on the spider. Okay, so even though our calculator spat out a negative sign at us, keep in mind that's because the spider is pulling down. But the question is asking us for the tension in the spider web. So the spider web itself is actually pulling up on the spider. So we're actually going to list our answer with a positive sign because that would be the scenario in which the spider web is pulling up. That's the tension force. So force is equal to, let's make this into scientific notation. So 7.84 times 10 to the, and how many times did we move that decimal place? 1, 2, 3, 4. Okay, and that's newtons. Okay, and that's how you do that problem. Okay, that's done with. Let's keep going. On to topic 5. So here's another very easy question. It's about vocabulary. So it says define the normal force. Here's kind of what I wrote as a hint to you. So be aware that normal force acts perpendicular to a surface that an object is resting on. So if I've got like, let's say I've got me and I'm standing on a flat surface. If I know that the force of gravity is pulling down on me, okay, let me get a green tool. So if I know that force of gravity is pulling down on me, let's call this F sub g for force of gravity. The normal force is the reaction force to gravity. So remember Newton's third law said that every action has an equal and opposite reaction. So because my body is being pulled downward with a force due to gravity, that it would make sense then that the floor is pushing up on my body with a force equal and opposite to the force of gravity. We call this force the normal force, so F sub n. Okay, so what I've written for you here is basically what I would say is the definition of normal force. Just remember, it always acts perpendicular to a surface, and it's also always acting in opposition to gravity. Okay, pretty easy stuff. Let's keep going. Okay, next one. What is the maximum frictional force in the knee joint of a person who supports 66.0 kilograms for mass on that knee? Now, I've given you a hint here. The coefficient of static friction hold on, I think I made a typo here. Coefficient of static friction for, I don't know why I put none here. I think I meant to put the word joint. I don't know why I got the word none though. That should say joint. Coefficient of static friction for a joint lubricated by synovial fluid is 0.016. Sorry about that. You can see the equation I'm giving you in blue here. So F sub F, the force of friction, is equal to the normal force, F sub n, being multiplied by the mu sub s, which is the coefficient for static friction. So very simple equation. You were just timesing two things together to get something else. However, in the problem, they gave us mass. You don't see mass coming up anywhere in that equation, do you? They want a force. We need to be able to plug in a force into this equation. So we have to remember Newton's second law: force is equal to mass times acceleration. And since the weight of this person is bearing down on this knee joint, we can treat the acceleration as being due to gravity, because gravity is pulling down on this person's body, which is stressing out their knee joint. Okay, so we can assume then that A is going to be equal to negative 9.8. Okay, so let's go ahead and figure out what the force on the knee is going to be. So force is equal to mass, which we said was 66.0 kilograms, times A, which is negative 9.8 meters per second squared. Okay, when we times those two things together, I take 66, I times that by negative 9.8, and I get a force of about negative 646.8. So equals negative 646.8 newtons. Okay, so we just calculated the force of gravity. Okay, so this right here is F sub g. Now remember that the normal force acts in opposition to gravity. Okay, so I can go ahead and basically flip the sign and say that the normal force is going to be positive 646.9 newtons. All right, so you got to be able to make a lot of these inferences and assumptions when you're doing physics problems. I'm now going to take my normal force, I'm going to plug it into the equation I gave you. Okay, right there. So I know that the force of friction from that equation, so F sub F is going to be equal to my normal force, which I just calculated 646.9, times by the coefficient of static friction, which I gave you in the problem as being 0.016. That was given to you in the hint section of the problem. So 0.016. If I multiply these two numbers together, I should get my friction force. Okay. So if I take 646.9 times it by my coefficient of static friction, okay, which means the force of friction that this joint is experiencing is about 10.35 newtons. Okay, so 10.35 newtons, and that would be your answer. Okay, right there. Let's keep going. I think after this problem, we'll take a break and do the remainder of the review in another recording, just because I have an appointment to get to very soon. So we'll get the rest of this to you later. Okay, so the last question that we're going to do today in this session: what are the magnitudes of drag forces at 70 kilometers per hour and 100 kilometers per hour for a Toyota Camry? Okay, assume the density of air is 1.21 kilograms per cubic meter. Drag coefficient is 0.28, and drag area is 0.70 meters squared. Okay, I gave you the equation down here you're going to need to use to solve this thing. Looks very complicated, but it's just multiplying a couple things together with squaring involved. So what this means is that the drag force, F sub D, is equal to 0.5 times C. Okay, C is your drag coefficient. Drag coefficient. You see this little thing that looks like a P right here. Okay, it's actually not a P, it's the Greek letter rho. I'm going to call it P though, just because I don't have a rho key on my keyboard. So rho is equal to is the density of air, which I gave you in the problem's hint. Okay. A, you probably guessed, is the area. And V, you already know, is velocity. Okay. So let's go ahead and plug in what we know. They're giving us a velocity right here. But remember, we need velocities always to be in meters per second, so we'll need to work with that a little bit. They're telling us that rho is 1.21. They're telling us that C is 0.28 and that A is 0.70. So basically, we're giving you much of everything you need to solve this problem. The only thing that needs to be challenging a little bit is just remembering to convert 70 kilometers per hour into meters per second. So let's do that real quick. Okay, so 1 kilometer is equal to 1,000 meters. 1,000 meters. Okay, and we mentioned earlier in this review, so I'm not going to go too deep into this, but we mentioned earlier that 1 hour is equal to 3,600 seconds. Go back and review the recording earlier if you don't remember how we got that. Okay, so let's go ahead, whip out the calculator, and I'm going to type in 70 times 1,000, okay, divided by 3,600, and I get a velocity of about 19.44 meters per second. Okay. All right. So we now have our velocity. We already were given the drag coefficient, the density of air, and the area. So all I got to do is plug everything in now. Okay, so the drag force, or F sub D, is going to be equal to 0.5 times my C value, which we said was 0.28. Multiply that by our air density, which is 1.21. Multiply that by our area, which is 0.70. Multiply that by the square velocity, so 19.44 squared. Okay, very long equation, but you're just multiplying, so this shouldn't be too bad. Okay, so in the calculator, let's clear this out. Okay, so I'm going to type in what's 0.5 times 0.28 times 1.21 times 0.70 times, and then we're going to do 19.44 squared. Okay, and I get a drag force equal to 44.8 newtons. Okay, that's how you do the problem. Not too bad. Just plug everything in and let the calculator do the work for you. So that's your answer right there. I'm not going to do the second part. I'm going to leave that up to you, but you would do the same thing just for 100 kilometers per hour. We just did one very similar to that. Okay. All right. So that concludes what I wanted to talk about this morning. We'll do part 2 a little bit later on today when we cover topics 6 through 10. It is a little bit shorter than topics 1 through 5 was, so it shouldn't take us too long to get through that. But practice these questions that we did today. You can use this recording to help you guide your study. And yeah, let me know if you have questions. Thanks so much, guys. We will talk to you soon.